Hello, everyone, and welcome back. We are going to start looking into a little bit more advanced topics, and one of the first ones is going to be embeddings. Why we want to talk about embeddings? Well, because we are going to be using vector databases. So right now, when we first started, we were passing over. We start testing like documents and passing those all over, reading those documents, and sending the entire set of documents to the LLM to ask questions or to get information within that document. In our case, it was small, it was 3 documents, and we were still only using one at a time. At the same time, we knew which document to retrieve because they are so small that we just could be playing around with each one of them. However, when you're in production, you will have like hundreds or thousands of documents, and they may range from images, videos, text, documents, Excel sheets, HTML. So there is a lot of different types of documents out there and different content. So what we're going to look is how do we start accessing these? How can we access them easier? How can we search through hundreds or thousands for the data that we have? Because it will then be efficient to open every single one of them to find information every time that someone asks a question, right? Now, embeddings are something that has been around for a long time. It's not something that came out with GenAI. It has been around for a very long time. And so we're going to take a look. Let's start taking a look at what does it mean. So text is something that humans can understand, but computers cannot. They don't know the meaning of what words mean. However, there is still certain things that we can do. And one of the first things that we need to do in order for a computer to understand words is we need to convert the words into numbers. And a long time ago, that conversion happened. Okay, you have a vocabulary of 200 words. I'm just going to convert each word to a list of numbers from 1 to 200. And that was okay to start with. But as we evolve these models and we evolve our understanding of how text works in machines, we came to realize that, well, text really, we can encompass a lot more in those numbers than just use a number representation. We can start doing the position of the word in a sentence. If it's a verb, if it's a text, if it's a person, an object, all of these different things that can tell us. And so we start looking into not only one number, but like multiple numbers that represent one word. And after that, we're like, well, we can also do sentences, we can do paragraphs. And so today, when we talk about embeddings, an embedding is a long list of words, long list of vectors or numbers. So when we're talking about embeddings, we also may be referring them as vector, as a list, or as an array. All of those mean the same things in the context of embeddings. They do have different meanings in other parts of technology, but in the context of embeddings, you will find that all of these mean the same thing: embedding, vector, array, or list. So let's take a look at what do they actually mean when we have a vector. So we have the text and we are going to convert it into a number. And this representation, this is a good image that I like. So let's say that you have the word fish, cat, bird, and dog. And for these, our embedding is a two-dimensional embedding. So we have the X and the Y. And so in that sense, for example, a fish, cat, bird, dog may be somewhere in the 3 to 6. 3 and 6. That's a 3 on the X, 6 on the Y, right? So we do 1, 2, 3, go up, and then we go 1, 2, 3, 4, 5, 6, more or less, right? It's not precise right now, but our embedding it's gonna be 6 and 3 and 6. Maybe fish is 2 and 5. Bird is 6 and 4.5. But all of them are in around this area. So my embedding and the numbers are going to be very close together compared to, for example, green, red, blue, and yellow. Now the embedding, the x-axis is going to be really far off, maybe 15, and the y-axis is going to be very low, like 1 or 2. And so these numbers are going to be very different. So in the x-axis, we have a very large number with a very low number in the y-axis. compared to fish, cat, and bear. So when you compare those embeddings, you will see that they are very, very different. And if you were to calculate the distance between the animals and the colors, this distance will be very large compared to the distance between bird and dog. So if you were to compare a dog to blue in our example, it will be way, 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 way farther away than if you were to do it between bird and dog. And so when we are converting embeddings, basically we are converting into these dimensions, x and y. This is a two-dimensional embedding, or or a list of two, or an array of two, or a vector of two. So in this case, you can see here on dimension one, it's telling me if it's how abstract or concrete the words are, and how positive to negative the words are. And so this is just an example. That doesn't mean that every embedding will have this, but you can have like whether it's a verb, whether it's a noun, whether it's an article, whether it's something that normally starts at the beginning or normally starts at the end, whether it's followed by a dot. Like there is so many different things. And so each one of them will be a value in that list. In our example, it's only two, but in reality, when we are using embedding models, that is a very long value. And it ranges from anywhere from 700 to about 2000. There may be models that have longer, but that's how many numbers in the list or in the vector there are. And so our brain cannot comprehend that if this is a two-dimensional vector, what it will look like a 1,000-dimensional vector. That will be like, that is, we don't work in that way. But at the same time, you know that each number in that 1024 represents something about the text that we are embedding, how abstract, how positive it is, how close to a verb it is, how close to a noun it is, how the words should be associated with each other. And so 1024 gives us a lot of representation, a lot of information about the text that we are embedding. In our example, we are also using only one word, but in reality, we can do full text. We can do one word, we can do full sentence, we can do full paragraphs, we can do an entire document. And also, we can do images. But it will depend on the model that we are using, whether what the embedding means. Right? So for text, it's very a lot of the times you use it like it's just the meaning of the text itself. But for images, it can be the objects that are inside, or it can be the style of the image, or both, depending on the model. Okay. Now, can you fine tune a model to be more attuned or better at certain topics? So, for example, if you're working in the medical field, you want to make sure that it knows every word in the medical field. Yes, you can do that. Maybe a generic model will not perform as well because it hasn't seen or wasn't trained in those words. Also, for example, in very specific industries, there may be slang or maybe terms that are very specific to that industry that you may need a special model for that so it understands it. But for the most part, a lot of the models that we have a really great understanding across all different domains. And they are very small. You don't have to necessarily run them in a server like LLMs. It can be run very efficiently and the full model in your local computer because they are very, very small. They are not trying to generate new wording, but rather just convert words and text into numbers. This conversion is part of an LLM. It's what it does at the beginning, but it's a very small part. So whenever you send a text to an LLM, it does this conversion automatically and then generates the text afterwards. But it does need to make this conversion. All right, so we have a little bit of a better understanding. So let's put it into practice. So I'm gonna start adding some code, and for this, I'm gonna start importing the libraries that I need. And so let me just bring up. So the code that I need, I'm gonna bring it here. This is gonna be my bottle tree. And so I'm just gonna bring it over here. And so I'm gonna have bottle tree. I'm gonna import JSON, NumPy, don't forget to install NumPy. I already installed it in my system, but you don't forget to install it. You can do pip install NumPy, like right here, and it will install NumPy. Don't forget to activate your virtual environment either. So that's important too. I import JSON, NumPy, and I'm going to import typing, import list and union, because this is going to help me with calculating the distance between my embeddings. This distance that I have here is going to help me. So I have all of these. I have imported my libraries. And the next thing that I'm going to do is like, well, let's start getting some embeddings in place here. So one of the first things that I'm going to need to do is my client, similar to what we did with LLMs. I need to initiate my client. As I was mentioning before, you can have an open source embedding, definitely, and download it and install it as your Python. You can have some of those embeddings. I'll have some links of some examples of open source embeddings in the description, and you will be able to take a look at those. But for us, we're going to use AWS. There are multiple embedding models in there. This is one of them, Titan Embed Text version 2. Depending on the model, sometimes you will be able to embed only text, and sometimes you will be able to embed text and images. If I'm not mistaken, this one can only embed text. I have my input body. Input text is my key, and the actual text that I want to embed is going to be my value. And so what I'm going to do is I'm going to send it, and the response is going to be pretty much just a string. I'm going to load it in JSON, and then I'm going to be able to get embedding out of that JSON. So I'm going to save all of that into my embedding. As you can see, it's very fast. Even if I had a large amount of text, it's going to be really, really fast because it's just a conversion and not like an LLM where it's trying to generate new words, which is the part that takes a lot longer. So I'm going to go ahead and I'm going to print this. I'm going to go and print embedding 1. You can see this is my entire list. So it's a long list, but all of them are in float. Now I can also print the length. That's going to be 1024, and that's the default for this model. You can also change it to a 720, and every model will have a difference. Now, can I use the embedding of one model and then use a different model to do an embedding of different text? No, because each model will give a different meaning to each of these numbers. So if I were to do this embedding of Titan Embed Detection in version 2, and I went, well, you know what, version 1, it's Titan, I will go ahead and do it. It won't work because, you will get embedding numbers, but when you compare them, they are going to be completely different. And that is because, similar to this, each of the models is given an arbitrary location for different words. That the fact that in this example, in this graph, the animals is in the top left corner, it's arbitrary. There is absolutely no reason why this couldn't be in the bottom or this could be on the right. It's just that for this model, that's what it's choosing to do every single time. So that is the consistency. Using the same model gives you the consistency of where in this dimensional space the words are going to be located. But if you start using different models, maybe in another model, this animal section is going to be on the bottom right, and this one is going to be really close on the top right. So it's going to be giving you very different results. And when you're doing calculating the distance between the words, well, it's not going to be really good, and it's going to give you false positives or false negatives. That something is really close when they are actually not. So when you're using embeddings, always use the same embeddings to generate your text. So the embeddings, can they work on their own? Like, for example, in this case, the cat is blue. I have one embedding, which is the list of text. Can I do anything with it? Well, not really, because the whole point of embeddings is be able to compare them or be able to process them. When you are using this in an LLM, these embeddings are being processed against all the knowledge of all the text that it has trained on. In our case, we can also use it to compare different texts. So for example, I can go ahead and I'm going to do a second one. The cat is green. Okay, and I'm going to save this as an embedding number 2. Now I'm going to print this, and it's going to give me this. Now, what does this one mean compared to that one? Well, we see that the numbers are different, but what does it really mean? That's where the calculating the distance between these two is going to come into effect. So I'm just going to go ahead and I'm going to copy a function that I had before. And this function calculates the cosine similarity or the distance between these two vectors. So you can see here it is converting the array into NumPy. NumPy is just a more efficient way to process and to do calculations on lists or arrays. And so doing the calculation, if you want to know more about how these are calculated, for example, the dot product, and this is matrix multiplication. I can add some links into matrix multiplication and a deeper dive into cosine similarity calculation. So it's doing all of this, and then after this, it's going to be doing kind of like normalizing it between 1 and -1, so it doesn't get out of this range. Now, why we don't need to know the specific of this, how this calculation works? Well, because this is an example. I'm just going to show you how this distance is calculated. But when you are dealing with production environments, you're not going to be calculating, like, for example, normally what will happen is like somebody has a question. That question gets embedded so that you can search it in a database. If you didn't have a vector database, then you'll have to do this calculation manually on every single row in the database. So if you have 1,000, the question that the user is asking will get transformed into a vector, and then that vector will need to go into this cosine similarity against all the 1,000 documents that you have in the database to find the one that is closest and then retrieve that, which is not efficient because every time that a customer will ask something, they will have to do that. And well, it will take a long time to be able to do it. And the more documents you have, the less efficient that is. And so when you have a database, a vector database, this is going to work a little bit differently, and you will have to worry about this part. And we're going to talk about that in a moment. But for now, what I'm going to do is I'm going to calculate the distance between my embedding 1 and my embedding 2. And so this is telling me that it's 0.71. So what does that mean? Well, anything close to 1 tells me that they are the same. And anything close to 0, anything close to 1 tells me that they are the same. Anything close to -1 tells me. Let's see if I do a third one. Now, instead of the cat, I'm going to do the dog. Okay. And I'm going to save it as embedding number 3. So now I'm going to compare my embedding number 2. Sorry, calculate. So I'm going to compare my embedding number 2 to my embedding number 3. That's because those are the most similar one. And I'm going to run it. Tell me that is not defined, but it is defined. That's because it's cosine similarity, not calculate cosine similarity. Okay, so I'm going to do this. And you can see that is 0.46. Even though we are only changing one word, the dog is green versus the cat is green. In our case, is making sure that the cat is green and the cat is blue is closer and refer to the same subject than the dog is green. Okay, and so this is the beauty of embeddings, that it allows you to really represent what the text is about. Let's do another one that is completely different. So I'm going to go ahead and I'm going to do a planet in the solar system. It's very big. I don't know, something random. And I'm going to save it is in embedding number 4. And then I'm going to calculate the, let's calculate this. So between embedding 1 and embedding 4. So that's point. So let's do now between embedding 2 and embedding 4, and between embedding 3 and embedding 4. So you can see here that all of them are closer to 0 than if they are to that they were in the previous ones, right? The previous ones were above 0.5, basically. And this one between embedding 1 and embedding 2, between the cloud blue and the cat being green, it's pretty close, 0.171. In embedding 2 to embedding 3, the dog and the cat is 0.46, versus in this case, it's really close to 0. So this is where you need to understand your embedding model so that you are able to choose a good threshold in which you say, okay, you know what, anything above this, I'm comfortable calling it related. Anything below this, I'm comfortable calling it not related at all. And so that is going to depend on the model that you choose and the text that you're embedding. And so I always like to make a few tests to make sure that my thresholds are good, because that's going to affect how I'm going to retrieve data. So what does this have anything to do with our document, our RAG system? Well, that is because we do have a very large documents. These documents that we have here are 4 or 5 pages. And so does it make sense that we open all of them? Does it make sense that, like, for example, in this case, sorry, let me change my screen so we can actually see one of these documents. So does it make sense that we are reading all of the entire document when we just want to know the key features of the bulldozer? Well, no, it's very inefficient for us to go through all of them, or being able to search for this particular document in among 1,000. Well, we can do the embedding of the entire document and it will retrieve all of it. But also, we can do an embedding. We can read the text and we can split it. We can split it into sections. This is one section. This is a second section. And these key features is another section. And so when we do a search, our question is going to get converted into an embedding. And then this information is going to be saved in a database where we are going to be able to do the search and just retrieve this part. So how does it do it? How does it know which part refers to what embedding? Well, if we take a look, let's go back here. And so in our database, what we'll see is that we'll have one column, which is going to be ID. And this column, and then it's going to be an embedding column, and there is going to be a text column. There may be more columns, but these are the basic ones that you need to have in a vector database. You can have other columns, metadata, additional columns as you need to. But in this case, this is what you may see in the database. One with an embedding, the 1024, and the text, the cat is blue, the cat is green, the dog is green, a planet in the solar system is very big. And so instead of you having to manually retrieve every single embedding and do the similarity or the distance calculation that we just did, well, the database already has that built in. And you can do a select, comparing the select on the similarity of this embedding. And it will automatically will go and do that similarity calculation and just retrieve the top 5 or the top 10, depending on what you select in your SQL statement. And that is going to be on the database to perform that. So when you are working with a vector database, in the documentation, you will be able to read what type of similarity calculation is going to do, because there are many different ones. There is the cosine similarity, there is the dot similarity, there is the Euclidean distance, and there is a few others. So in the documentation, you will be able to read which type of distance is going to be able to calculate when it's doing the search. Sometimes you can specify your own, sometimes you don't have an option, and it's up to the database to do the most efficient one. That is what's happening. And once it finds the closest one, then it's going to retrieve the text on the side. And that is the text that you're going to send over to the LLM. So your final LLM, the LLM that is going to do the actual reasoning or the actual summary, it never sees this embedding. This embedding is just your method to find this text. And so that's why we can use a model, a specific model for the embedding and a different model for doing the reasoning, even though both of them are doing embeddings, because the first embedding model doesn't is just for the search of the text, just to find the right piece of information and then send that piece of text to the model that is actually going to answer your question. Okay, so that is what is happening in database. That is what is happening in the backend. There are many different databases that can do this. You can have Postgres, you have Aurora, you have Chroma that you can install locally to be able to do this. But you can have others, like for example, graph databases like Neo4j or Neptune in AWS. You can have Pinecone, that's another one. And there is a lot of other databases now that are out there. WaveNet is another one that has a vector database embedded into it. And so all of them have their strengths. All of them have some issues, but it's up to you to be able to find one. And so in our next section, in our next episode, we are actually going to stand up database, and we're going to go for use a couple of them. Okay, we're going to use an Aurora and we're going to use an OpenSearch one, and I'm going to tell you why. And you will be able to take a look at what's happening behind the scenes on these two services. But for now, it is important for you to understand what these embeddings are so that we are able to implement a good technique and a good strategy when we are building our application with the services. Okay, so I hope you have fun. Keep having fun because this embeddings on its own is quite powerful. I have delivered solutions that do not need to use LLMs and they only need to be using embeddings. And they are performing really, really well because it allows us to do text search when the text search doesn't have to be specific or cannot be specific, but rather it has to be closer in similarity to the meaning of the text that you're doing rather than the specific words that are being used. Okay, so I hope you're having fun. Keep going through all of these. I'll be sharing the next episode soon. Well, if you have any questions, please let me know.